So first of all, thank you very much for inviting me to present at Materials 2023. It's a pleasure to be here again. I presented in last year's meeting, and I'm very happy to be here today. So this time I'm going to talk about polyoxometalates as electrocatalysts for rechargeable metal air batteries. And this work has been done in a collaboration between Portuguese and Serbian groups. So as you know, we're discussing very well in the last few years this problem with the increase of temperature, the overall temperature. We know that human influence has significantly warmed the climate, so we need to find ways to decrease this problem of of the temperature increase. There is a lot of work on developing more renewable energy sources to decrease the consumption of fossil fuels. But to have sustainable energy production is also necessary to have sustainable energy storage. And for energy storage, batteries are essential. For this specific work, we are working in a very interesting way to store energy, which is on metal air batteries. These systems are very interesting because they have very high energy density. How does this work, Lauk? So these metal air batteries, they have the advantage that they work in aqueous electrolyte. It's an advantage to, for example, other batteries like lithium-ion, where you use organic electrolytes. Here, it's more environmentally friendly. What we have is the oxygen reduction at the cathode side. As you see here, oxygen coming from air is reduced on the cathode side, and at the same time, here, put the pointer. On the anode side, we have a metal anode that is oxidized and loses the ions. So this is the process working on a metal air battery, and we are specifically working to the development of rechargeable metal air batteries. This means that the metal air battery is not just a primary system, but it can be recharged and to recover the metal anode. And during recharge, of course, instead of the oxygen reduction, during the charge of the battery, you have the oxygen evolution reaction. And this has been our main focus for this work, to develop at the same time a material that is active for the oxygen reduction during the battery discharge and for the oxygen evolution during the charge. So these devices are very promising, and as I said, like the electrolyte is aqueous, so they are safe. They have lightweight. They are cheap. So they have several advantages. Briefly, just to mention, one application of metal air batteries that is currently being used is, for example, for hearing devices. For hearing devices, you have those very small batteries that they are actually metal air batteries. So this is a very important application. Why did we decide to use polyoxometalates? Lately, these polyoxometalates are showing a lot of interest for different applications because they have very low charge transfer resistance, they have high thermal stability, high resistance to oxidative decomposition, and they can be coupled with high surface area conductive carbons. So why do we do this? Because conductive carbons, they increase the electronic conductivity of the materials, and if you produce a composite of the conductive carbon with a polyoxometalate, you are able to produce a composite material with very interesting properties for electrocatalysis. So that's what we did here. We synthesized 5 different metal polyoxometalates. We did the characterization of those materials by XRD, Fourier transform infrared spectroscopy, SEM, EDS, and then we did the electrochemical characterization because we are working in electrochemistry group, collaborating with other material science groups that do also work on the synthesis, which was mostly done in Belgrade, and here in Lisbon we did the electrochemical characterization. We also did a construction of a small lab metal air battery that could test the developed materials. How do we do the experiments? So basically, we first produce the materials, then the POMs, they are put together with the conductive carbon in a composite. The material we selected for carbon was reduced graphene oxide. Reduced graphene oxide is very used in electrocatalysis due to its high electronic conductivity, very interesting properties. So we prepared different composites between RGO and these different POMs. So after we prepare these materials, we make a catalyst ink. So the ink is based with a small amount of catalyst. Then we put water and ethanol and naphthalene that works as the binder to bind the catalyst to our electrode surface. So then we just simply put a small amount of this material on the electrode, like 15 microliters of this ink. We let it to dry for 10 minutes in the oven at 50 degrees Celsius, and the electrode is ready for the electrochemical testing. This is the experimental apparatus, very simple for the typical electrochemical studies, with the reference electrode, our working electrode, and a platinum coil as the counter electrode. This is the characterization of the 5 different transition metal POMs. This is the SEM analysis of the materials, and here is the XRD and FTIR analysis of the POMs with the RGO. So the final electrocatalysts that we tested, and this characterization showed that the materials were prepared as aimed. Then the electrochemical measurements. How do we do them? Basically, after we prepare the electrode that I just mentioned, we put this in an 8 molar KOH solution, which is the typical electrolyte solution used in alkaline water electrolysis for hydrogen and oxygen production by this electrolytic method. And we run the polarization curves into the anodic direction because we want to test this material for oxygen evolution reaction. And we see here that the 5 different POMs, they have very different behaviors. Like copper POM was clearly the worst material, and cobalt and nickel POMs, they have the best performance for oxygen evolution reaction. We did not only the direct polarization curves, but also the ohmic drop corrected polarization curves, because when you do electrochemical experiments, there's always a small distance between the working and the reference electrode, and you have to deduct that ohmic drop so that you can have more accurate data for extraction of the kinetic data. So you have a more accurate analysis of the produced data. So here we show the different materials, and then we get what is called the TAFEL analysis. So we do the TAFEL analysis to get the TAFEL regions, and from the slope of these TAFEL plots, we have the what is called the TAFEL slope. Here we see that the one, as I mentioned, for copper was quite bad, but for the other materials it was quite interesting. Like manganese, copper, and nickel, they had good results for in terms of TAFEL slope. In terms of onset potential, which means like the potential from which the oxygen evolution reaction starts, that we want to be as low as possible to reduce our electric consumption. And we've seen that for the nickel POM, it has the lowest onset potential for oxygen evolution reaction, which is very interesting. So this shows the best activity of the nickel POM, which is consistent with what we observed with this impedance data. So these are the Nyquist plots that show the electrochemical impedance spectroscopy analysis, and we have much lower impedance here for the nickel POM. So the charge transfer resistance is given by the diameter of this semicircle, and as you can see, it is much lower for the nickel POM and then followed by the cobalt POM. So these were the most interesting materials for oxygen evolution reaction. So this shows again like what I was focusing, and here we see clearly the charge transfer resistance for the nickel POM was much lower than for the other materials, showing the good activity of the nickel POM. Then what we did was, knowing that the nickel POM was the most interesting material, we decided to test different ratios between this POM and reduced graphene oxide. So what we did was to change the ratio between these two components in the prepared composites from 1 part of POM to 5 parts of RGO until 5 parts of POM to 1 part of RGO. And preparing those different ratios, we could try to assess what was the best composition for these materials. And what we could see here was that, of course, we also tested just the nickel POM without the RGO and just the RGO without the nickel POM. And it was very interesting that the material with the best performance was this 1 to 5 nickel POM with, well, 1 part of nickel POM to 5 parts of RGO. It had the lowest Tafel slope. It had also a low onset potential, and the current that was recorded at an overpotential of 400 millivolts was the highest. Like at 400 millivolts, we had over 83 milliamps per square centimeter, which was very interesting. This was even better than iridium oxide. This iridium oxide is the state-of-the-art material, which is used for oxygen evolution reaction. It's an expensive material based on a noble metal, but it's being pointed out and widely used as the best material for oxygen evolution reaction. And in this case, we got better results for OER than benchmark iridium oxide. So here we have a comparison of the different materials and the Tafel slopes that I was showing, and this also compares with the literature that was found with similar materials. So our results were very promising for oxygen evolution reaction. Moreover, if we consider the price of the catalyst per unit of current, we see that considering the higher currents also that we have managed to produce with this composite, the cost of the material per unit current was lower than the one from iridium oxide. So this was very interesting results here. Like basically, if you consider the prices also, like from Aldrich, for example, the material that we tested is much cheaper than the iridium oxide if we consider their performance. We also tested for the oxygen reduction reaction, and for the oxygen reduction reaction, nickel POM has interesting results, but cobalt POM was even slightly better. So these two materials that had been the best for oxygen evolution reaction, they were also both good for oxygen reduction, being the cobalt POM the best one. So these are the reactions involved in oxygen reduction reaction, which is also a 4-electron reduction. And we see here the Tafel slopes that we measured, with cobalt POM being better with a slightly lower Tafel slope. The number of exchange electrons here was closer to 3, and here was around 2. So meaning we are not being able to get the 4-electron reduction reaction, which is the aim, but still it was very good. Then to finalize, we built the metal air batteries, and the results with the metal air batteries were very interesting, specifically with the one where we use this cobalt POM. So the cobalt POM had the higher power density during the discharge. So like we managed to attain like 30 milliwatts per square centimeter during the battery discharge. So these were very interesting results. And besides that, we also tested with different electrolyte compositions. And it showed us that the higher power densities were obtained also with the concentration of electrolyte of 4 molar KOH. So with the increase of electrolyte concentration, power densities also increased. So just to summarize, this study focused on the use of polyoxometalates as electrocatalysts, as they were cheap and easy to obtain, much cheaper and easier to obtain than noble metals, that they are scarce. And in conjugation with carbon materials, we managed to increase the conductivity of these materials. We saw that the nickel POM 1 to 5, like 1 POM to 5 RGO, was the most active for oxygen evolution reaction, and for oxygen reduction reaction, it was the cobalt POM. So, and we also saw that when doing the tests in the metal batteries, the cobalt POM was the one most active. So, because of this, considering that cobalt POM was the best for ORR and the second best for OER, we assume that for application in metal batteries, CO POM seems the best bifunctional electrocatalyst for these devices based on these results. So I can quickly show you if this works. Let me see if I can put, okay. Just to show you that our metal air batteries, they actually work. So we were able to connect here to some LEDs and to show you that during discharge, the battery actually works and it is producing energy. So I hope that this can be transposed for really practical applications of these materials. So, oops. Okay, I think this went out. Okay, so this was just my last slide, and okay, just to thank you for your attention. There is my email and contacts in case you want to address me some questions or possible collaborations. Thank you very much for your attention.